Hello everyone to this new video about OpenGl ES. In this video I will be showing how to draw basic kinds of meshes. In the previous video we already refactored our code and we created this position object and used it to draw a rectangle. In this video I will be using the same object to draw a cube, and then we will create a new object. I will call it BCT object, that stands for position, color and texture. That means the buffer of this object will not only contain position data, but also color data and texture data. And I will also use this object to draw a cube with a texture. I will also show in this video how to draw a wireframe in OpenGl ES. On the desktop, you can use the GL function, GL polygon draw mode, and set it to lines. This will draw the edges between the different vertices of your object instead of drawing a filled triangle. And of course, you can use the same function to set the draw mode back to fill. That will draw the whole triangle. Unfortunately, this function is not available in OpenGl ES. So to get around that, there are actually many solutions. The one I chosen here is to generate a line mesh from our current mesh. So for example, for a cube, we will need 2 triangles per face, and we have 6 faces, so we will have in total 12 triangles. Each triangle will contain 3 lines. That means in extracting lines, we will be extracting exactly 36 lines, and we will be drawing them. Before we start doing these meshes, I already did some small changes and refactoring on our last code. So I decided to save the texture, for example, in the assets folder instead of the drawable folder in the resources. That's because the resources folder does not allow creating subfolders there. And you will see that have an implication that now I will be using the path of the image in the assets folder as an ID. The second change is adding a callback for the update function on the objects. So if you want to implement something on update objects, instead of having to derive from that class and implementing the function update, now you can add a callback, as I will show later. Let me go now to the code and show you these changes and then start introducing our new meshes. As you can see now here in Git, I'm displaying the files which has been changed. So the first thing, as you can see, I already added this callback called iObjectUpdate callback, an interface which contain only one function called update, and this function will take as a parameter a timestamp and object. Get this update object callback, we only need to implement this function and pass this callback to the object. In the abstract object class, as you can see here, I already now included a member variable which will hold this update interface, and you can set this callback by using this function set update call. And now in the function update, we check if the update callback is not null, then we call it. And then we call the abstract function on update, and this will call the normal update of our P object if we want to add anything here inside this function. As you will see later, for the P object, this on update is still empty for now. We did not implement anything there. And now instead of having the update function to be abstract, we called it now on update. So previously we have this function translate. As you can see now here, I added a new function called set translation. So that the translate functions looks where the object now and shifted by the XYZ vector, while this set translate function does not care about the current position of the object. It just goes and override this position using this new input vector XYZ. You will see this function set translation for matrix 4, which I implemented inside the matutil class. I also changed the rotate matrix function. So previously I used this set rotation Euler M2 from the OpenGL matrix class. Unfortunately, when I tried to run this code on an old device, it did not work. So now I currently changed it to rotate M. Maybe I will change that even later to a function inside our utilities, depending on how things go. Now in the position object, as you can see, the only change here that the abstract function is not called update anymore, but on update. So in the scene class, there are some more changes. First, regarding the texture, as I said, the texture now will take a string, which is the path of the texture in the asset folder. And now our map here uses the string as a key instead of an integer. Same here for the load texture function. We will pass a string. I also decided to move some of the draw functionality to this abstract class here, since this function is not related to the input. Remember, we created this class called scene, which derived from this abstract scene class to hide the GUI stuff from our core objects. However, those things are related to our 3D scene and to OpenGL and has nothing to do with the input. That's why I decided to put them here. So now in the scene class, as you will see here, so we do update frames per second and we output that, and then we do the error check. Then we call the draw function of our abstract scene, and this will do the clear update objects and draw objects. Now in the texture class, as I mentioned before, so we have a path of the image instead of the image ID, and this path is used to load the texture, as you will see here inside this send texture to GL. So inside this function, I put now the code related to generating the texture ID inside this function called generate ID. Then we bind the texture. Then for loading the bitmap, I call this function get bitmap from asset, and this function in the utilities. I will show you this function later. And the rest is as before. We set the parameters and do the bitmap and recycle our bitmap. In the program class, there was only small change I did here. So the offset should be actually here in bytes, not in floats. So I had to multiply here. So this was a bug. And I added this function set uniform integer. So previously we had this function to setting a uniform of 3 floats. This function will set a uniform, which is an integer. So we went through all these classes. The only thing left is the utils and the mat util. So in the utils, as you can see, I only added this get bitmap from asset, and it's similar here to this read asset file. So it get the asset managers and use it to open the file path and then read the bitmap, then return it. And in the mat utils, I already, as you can see here, I added this set rotate Euler 2 function, which I copied from the OpenGL matrix class. And I added more functions to do operations on matrices and vectors. As you can see here, the first function is set translation matrix. So this function takes a matrix which is 4 by 4 and sets the first 3 entries of the last column in this matrix to the given x, y, and z values here. The add function is simple. It takes 2 vectors and just add them. The subtract does the same. However, it subtract these 2 vectors. The scale function, it take 1 vector and it scale its values with the corresponding scaling factor here s. The norm function computes the norm of a vector a. The normalize function takes a vector, it computes its norm and then divide by it. So now this vector a will have a norm of 1. This function cross compute the cross product between 2 vectors a and b and return it. Cross product only defined for vectors in the 3D space. If the vectors a and b has more than 3 entries, those will be ignored. As you can see here, we are only using the entries 0, 1, and 2, and the value returned will contain only 3 values. Then we have this function make a new copy, which take a vector and just create a copy of that vector and return it. We have the function rotate vector 3, which takes as an input a vector, an angle, and an axis. And we want to rotate this vector v around this axis by the given angle. For that, we construct a matrix, a 4 by 4 matrix. We set this matrix to be the corresponding rotation matrix around the given axis with the given angle, and then we do a matrix vector multiplication. The matrix vector multiplication function simply takes a matrix and a vector and the number of rows in the matrix. This is because we need to know the dimension of this matrix. And then it performs a matrix vector multiplication and return the result. The angle function computes the angle between 2 vectors. This function uses the dot product because the dot product equals the norm of the first vector multiplied by the norm of the second vector multiplied by the cosine of the angle. So now if we computed the dot product and divided by the norms of the vectors, we get the cosine angle between these 2 vectors, and then we can use the arc cosine function which will return the angle corresponding to this cosine. This angle will be between 0 and pi. So what I'm doing here is shifting this angle to be between minus pi over 2 to plus pi over 2, and then converting it to a degree. The dot product is just is simple. We just multiply the corresponding entries of these of the input vectors and sum it. And that's all for these changes which I did. I hope that's not too much. If you find any problem with that, please write me in the comments and I will answer your questions. Now, as you can see, we run our program and we have the two rectangles which we drawn last time. Now let's start drawing our basic meshes. And in this tutorial, we'll be drawing a cube. So as you remember from the previous tutorial, we already have this position object, and this object is able to draw a list of triangles represented by these vertices. What we need to do to draw a cube is to create the vertices corresponding to the 6 faces of the cube. And for that, I will be adding a new class here. I will call it CubeVert. In this class, I will have vertices of the cube. I already prepared this. As you can see here, I started it by the two faces which are parallel to the x-axis. So this is the first face, this is the second one. You can see that those parallel to the x-axis, since this face has all the coordinates minus 0.5, which means it's parallel to the x-axis on the negative side. This one will be parallel to the x-axis on the positive. Similarly here for the y-axis, we have one parallel to the y-axis on the negative and then to the positive, and later for the z-axis. I also add this function create. This function will take 3 floats as an input. These variables will tell us how long we want each dimension of this cube. So on the x-axis, y-axis, and z-axis. And the function is simple. We just create a float array, which is the same length as the cube vertices here. Then for each dimension, we copy the corresponding column. So that would be first the x column from the cube vertices to the float array rate, which we want to return. And then we scale this column by the corresponding scale factor. So this I first would be 0. That means we are copying the x-axis, then scaling that. Then 1. That means we are copying the y coordinates and then scaling them, and so on. That's all what we need. Now we can go to our main activity, and let me comment these 2 lines here. For creating a cube, we only need to create an instance of the class pObject, as you can see here. And in the constructor of this pObject class, we pass the cube vertex, which we get from this createCube function for the vertices, and then the corresponding color. I think this function is called only create, and as you can see, we are creating a cube which is large on the x-axis, smaller on the y, and the smallest dimension would be on the z-axis. That's it actually. We already now have our cube. We just need to add it to the scene. And let's run. So we have our cube, but it's too big and maybe close to the camera. Let me move the camera back. So this is our cube. So to get the feeling of this cube, let me add now a rotation to it. So if you remember, we already added this function, set update callback, and for that we need to implement the interface I object update call. And there we have only one function called update. Let me make this as a lambda function. And I only want to rotate this object. So basically I just rotate the object with 1 degree around the y-axis. And let's rerun. Let's move away from the cube. Let me make this cube a little bit smaller. So now it will have the same dimension on all 3 axes. Now for creating a new kind of object, we only need to create the vertices, and this class pObject will take care of the rest. Let me now add a new object type. I will call it BCT object. So as I said in the introduction, this will be position, color, and texture object. I already prepared the code of this class. Let's go through it. So the same as before, this class will contain a program. We will not be using the colors. It will also has a reference to the vertices, and it will have a vertex buffer, and we'll have some booleans here to decide if it has colors or texture. So I will allow our vertex buffer to contain positions and colors, or positions and texture, or position and color and texture. That's why we have these 2 boolean variables here. Then we also have the texture and the texture path, and we will not be using this wireframe for now. So the constructor is simple, just take the vertices and these Boolean variables and the texture path. So we set the member variables to the corresponding input. For the stride of our buffer, we first start with the number of float spear positions because our vertex buffer will always contain X, Y, and Z coordinates. Then if we adding color to these vertices, we will add the number of float spear color. And if we're having a texture, we will add the number of float spear texture. And the number of vertices which are saved in this buffer will be simply the lengths of this input vertices divided by the stride. Before we go in the onInit function, let me show you the changes I made to the fragment and vertex shaders. So in the vertex shader, I added these two integer variables, has color and has texture. Unfortunately, in the shader language, I was not able to find a Boolean. That's why I used the integer type. Inside the shader function, I will set these two output variables, which are also integer, to the input to the uniforms, has color and has texture. So if the object has a color, this out has color now would be a value of 1, and then we will output the color as the corresponding color, and if it has a texture, we will output the texture as also the corresponding texture. This GL set point sizes was just an experiment which I was doing. It's not needed. Now in the fragment shader, we will get our output from the vertex shader, which are the color, texture, and these two Boolean variables. So to compute the output, which is the fragment color, first I set it to ones. Then if we included a color, then I multiply this fragment color with the corresponding color. If we has a texture, I also multiply it now with the corresponding texture, then return this fragment color. Basically, the only change here is that I'm always checking if we has a color or if we has a texture. Now, as you can see on the onInit function, I load this program, then create the buffer and load the vertices, then use the program. Then I need to set the different attributes. So the first attribute would be the position, the same we did on the P object. Here, however, we need to check if we have a color. Then we also set the attribute of the color and we increase our offset. This offset will be used here in the attribute on each attribute. So it will start by 0, then will be 3 by 4, then will be 3 floats multiplied by 4 bytes per float, and then will be more, depending if we has a color or not. Yeah. So as you can see here, then if we have a texture, we also set the attribute a texture with the corresponding offset, and we need also to load the texture. Yeah, for now I will not be using this wireframe. That's it. So the only thing which maybe I explained wrong is this current offset. Now this current offset here will be in floats, not in bytes, and inside this function set float attribute, we will be taking this offset in floats, then we will multiply it with the number of bytes per float. The onUpdate and destroy function still empty. Now the draw function. In the draw function, as before, we need to use the program and the buffer need to be bound. Then if we has a texture, also we need to bind the texture. Then we set our uniform. So this should be integer. Those will be float here. I will put them to integer. So if this float is true, I will put the integer to be 1. If it's not, I will put it to 0. Same here. Then we need to set our model view and projection matrices. And finally, draw the triangles. This wireframe stuff we don't need now. So let's go to our main activity and make our texture cube. I already prepared a texture for it. So this texture I will save here inside the assets, inside the subdirectory called images. So this is the picture. This picture contains 8 squares. Each square is numbered and with a different color. I will render each one of these squares on a face of our cube. So we'll be using 1, 2, 3, 4, 5, and 6, but not these two here. For that, we need to provide the corresponding texture coordinates. So instead of having the texture for each cube going from 0 to 1, it will goes from 0 to quarter on the x-axis and 0 to half on the y-axis. And then we have to increase that to get this second face. We need to start the x by quarter and end by half and so on. Yeah. I already prepared a function which will do that. inside this cube vert class. So this function called create with one file texture, and it will take as an input as before the x, y, and z scales, then the number of columns in the texture and number of rows. So for this texture, we have 4 columns and 2 rows, for example. Then the same as before, we will initialize our returned vertices, and we copy the x, y, and z positions to it. Then we need to match the texture coordinates. For matching the coordinates, as you can see here, I am looping over the vertices, and each time I will take the 3 vertices corresponding to the current triangle. Then I will create temporary variables to hold the texture coordinates, and depending on which phase we are in, so if the vertex index is lower than 12, so we are in the first 12 vertices which are parallel to the x-axis, we run this code. Then if we are in the parallel to the y-axis, we just here run this code, and this will be for the z-axis. And the main function here is the match texture function, which will take the x, y, and z positions of a vertex and the number of columns and rows in the texture and return the corresponding u and v coordinate of the texture. This is the match texture function. It's really straightforward. It takes these corresponding coordinates that we want to attach the texture to, and compute the step we move over the u and v. That depends on the u, on the number of columns, on the v depends on the number of rows in the texture, and then return the corresponding u and v coordinates. Yeah, and that's it. Now we can create our cube with texture as before. So in the main activity, we get the vertices with a texture. As you can see here, we are putting the scale to 1, and the number of columns in the texture are 4 and 2. Then we create an instance of our BCT object. We pass the created vertices, and it does not has a color. It has a texture, and the texture is in the images 8color.png. So that's it. We can now use the update function also to rotate this object, and then we need to add it to the scene. Let's run the program. So as you can see, we already have our cube with the texture. Let me move a little bit away from the camera. However, you see like some weird artifact. This is because we don't have the tips function set correctly. Let's solve that. So the best place maybe to do that would be the scene function inside this onSurface created. So we can add this GL call. We ask the OpenGL to enable the tips test. And now let's rerun. And now as you can see, the image is displayed correctly and the faces are not mixing. Previously this tips function was not enabled, then the faces are drawn in the order that we add them. And that's why always one face stays on top of the others, no matter which direction our rectangle is. So, and that's it now for creating a cube with a texture. Now let's handle the wireframe. For the wireframe, I already prepared a custom object. I called it wire object. Let me add it inside these custom objects. So similar to the P object, this object will have a program, color, vertices, and vertex buffer. It will have the number of lines instead of the number of vertices. The number of vertices will be the double of that, and the stride in float and the line width. I'm setting it to 20 as default now. So as you can see here, the stride will be only the number of floats per positions, because we will not be adding any colors or any texture to this wire object. It will just be vertices, and we will connect them with one uniform color. We have the function setColor to set the color to this wire object, and then we have two functions to construct this wire object. One function called setVertices from triangles buffer. So this assumes as an input an array of floats, and inside this array of floats we will have vertices which represent triangles. And then we have this set vertices from past function. I will not be using this function in this tutorial, but maybe in the coming tutorials. This function will assume that this vertex array contains vertices which represent a path. Imagine that you want to draw a circle, then you will have multiple points and we want to connect them. And these points will be represented inside this input here. Let me go through the set vertices from triangles buffer function, because this function we'll be using now. So as an input, we will have the float array, which contains vertices representing a rectangle. These vertices could have a color and or a texture. That's why we need here the offset and the stride. I will start the vertex buffer by the position. So that's why this offset will be 0. And we also need the stride. The code is simple. We compute the number of lines. That would be the lengths of the vertices divided by the stride. And that would be actually our line count here. And we need the vertices buffer to hold double those vertices. And now we have here times 3 because we will have x, y, and z coordinate for each vertex. Then we want to loop through the vertices. So each time we get 3 vertices. So this is x, y, z for the first ones, for the second one, and for the third one. This is from the input vertex here. These 3 vertices will represent one triangle. So for this one triangle, we need to create 3 lines. And this is what we do here. So as you can see, we assign the x, y, and z of the first vertex, and we want to connect it to the x, y, and z of the second vertex. Then we need a line from the first vertex to the third one of the triangle, and then between the third one and the second one. And that's it. In the set vertices from past, the code is very much similar. However, since we will be connecting the points inside these vertices, which represent a path, we will take each time the current vertex and the vertex next to it, and then we connect a line between them. And that's it for this function here. Then the rest is as before, as in the B object. So in the onInit, we need to create the program. For this, we will have this wireframe program. Let me show you what's inside this program. So inside the vertex shader, we have an attribute for the position and a uniform for the color. The same also uniforms for module, view, and projection as before. And of course, we will be outputting one color. This color will be set to the uniform color, and the position as before is the multiplication of the position with the model view projection matrix. In the fragment shader, the output color will be simply set to the color which we get from the vertex shader. That's it for this. So then we need to create the vertex buffer and load the vertices to it. Then we use the program and we set the attribute position. Update and destroy functions are empty. And in the draw function, similar to before, we need to use the program, bind the vertex buffer, set the color, and set the model view matrix. And then we need to draw lines. For drawing the lines, we are calling this function draw lines, which I will add inside the A object. So this function take the first vertex and the last vertex. Mostly we'll be passing here 0 and the count of vertices which we have. So basically the number of lines times 2 and the line width. And it simply calls the GL function to set the line width, and then calls the GL function draw arrays, where now the draw primitive is lines, and of course between the first and last count. It's very much similar to this one here, except for using the primitive type to be lines. That's all for the wire object. And now we can use this wire object inside our main activity. We first need to construct an object of the type wire object. We can also assign a color for this object. Then, as I said before, we will call this function set vertices from triangle buffer, and we will pass the vertices which we created. The offset needs to be 0 since the vert object starts with the x, y, and z position, and the stride should be 5, which are the number of floats per position plus the number of floats per texture, since this buffer will contain only positions and texture. And that's it. Now we can add this wire object to the scene, and let's run the program. As you can see now, the wire object has been created and drawn. However, it's not being rotated with the cube. For that, we need also to add this update call here, similar to the cube. And let's rerun. So now you can see that in each face, we are drawing 2 triangles. And this is actually very good to debug your meshes when you have a very complicated mesh and you have an error there. That's all for this tutorial. Thanks for watching, and see you in the next one. Bye.